Hi, everybody. It's Mr. Alsop again, coming to you from my amazing home studio. Uh, just coming back with some more science for you this week, trying to teach you guys a little bit about some of the middle school science that we typically learn in seventh grade. Sometimes some folks get this in eighth grade, sometimes some folks get this in sixth grade, but it's kind of the middle school level on science. So if it seems a little bit basic for high school students, that's probably why, because it's meant for middle schoolers. But that's what we do. So, taking a look today, we're going to take a look at an interesting figure in science. We're going to take a look at Darwin, the science superhero over there. A lot of people, when you say Charles Darwin, that's the image they get of him. Old guy, big beard. In this case, he's wearing a cape, which is why I said he's a science superhero, because only superheroes wear capes, right? Normal people just don't walk around during the day wearing capes. Do like the choice of hats too, kind of nice. But this is the picture we kind of have of Darwin. And we're going to talk a little bit about some of his ideas today and some of the ideas that he kind of brought to us as scientists. But before we do that, there's something I always like to talk about whenever we talk about any famous scientist and we talk about any kind of famous scientific knowledge that we've got. And that is, I like to talk about the person behind it. And so Charles Darwin, when you look at him here, you see this kind of image of him as an older person with the long beard. He looks kind of cranky. You imagine he's probably like your grandpa. Um, and that was true of him in his later life. But in his earlier life, he's a very different person from what you see here. He was young at one point in time, like all of us were. And I know my students in my classroom, when I tell them I was young once, they're like, no, no, you weren't. You were never young. You've always been old. But uh, Charles Darwin was young at one point in time. And we don't think about young people and the young scientists that are out there. And a lot of times we think of ourselves and we say, well, the way that I was when I was in high school, there's no way I could ever be a scientist. But when you think about people like Darwin, Charles Darwin, when he was in college, he actually got in some pretty serious trouble for some things that he was doing in his apartment with his friends when they would have parties. He would get together with his friends, they would have these big parties in his apartment, they would get really loud, and they would do dumb things. He got in really big trouble because he used to have a bullwhip, one of the like the big whips that you use to uh, he had a bullwhip in his apartment and he would stand out on the balcony. He was on the second floor. And this was back in the 1800s, and people in the 1800s loved to wear those big giant hats and stuff like that. He would stand on his second floor balcony and look down on the street and watch for someone with a cool hat to walk by. Like, ooh, look at that hat. And he would take his whip and he would whip their hat out into the street, off of their heads, just and their hat would go flying off of their heads and it would go flying out into the street. And back then, most of the stuff that was in the street was from horses. So there was a lot of manure in the streets, and the hats would get ruined, and people would get really upset. And some people even thought because of the snap of the whip, it sounded so much like the crack of a gun. People thought that he was shooting at people from his balcony. So he got into some pretty big trouble for that, along with some other stuff where he actually did one of his other favorite games with his friends is they would stand one person on either side of the room from each other, and they would put candles on top of their heads, and then they would get pistols. Back then, they had the pistols back then were not like they are now. They had muzzle loading pistols, and they would get muzzle loading pistols, and they would load up the pistol, but they would not put in the shot, the ball, the actual lead ball that goes into the pistol. They would just put in all of the cotton wadding and they would put in all of the gunpowder. And then they would stand across the room and fire these pistols at each other to try to blow out the candle on top of each other's heads. Um, so that does not sound like the kind of thing that a genius would normally do. Uh, and there are a lot of my students, when I tell them about stuff like this, they're like, wow, that's really not a good idea. And I'm like, yeah, that's really not a good idea. So don't ever try to do any of the things that Darwin did when he was a kid. But the reason I tell you about them is because we have this image of scientists as being these old men who've always been kind of, ahead of their time and always have been super scientific and super scientists and they've always been like that. And that's just not the truth. A lot of these people in their early years were every bit the rebel and the outcast and the criminal that maybe some of you can identify with. Maybe some of you have felt that way. You felt like you're the one that always gets sent to the principal's office in school. And that doesn't mean that you can't be a great scientist someday. It just means that right now in your life, you have some things going on that maybe are making it harder for you. But we can always overcome these things and can rise to the level that our intelligence can bring us to. And even the intelligence part is not always necessarily the greatest thing. Even Charles Darwin said of his intelligence that he felt that really, if he made any contributions to science, they were because he watched what went on around him and had the patience to see things happening. And so he never thought of himself as being particularly smart either. So even if you don't think you're smart, even if you get in trouble all the time, you could still someday be a great scientist like Charles Darwin. So think about that when you think about science and when you think about, oh, I could never be a scientist. You can, because not all scientists are the same. So with Charles Darwin, one of the big questions we want to answer is this idea of natural selection. What is natural selection? And when we read what New York State wants us to learn about Charles Darwin, they want us to be able to use mathematical representations to support explanations about how natural selection may lead to increases and decreases of specific traits in populations over time. Woo. That sounds really complicated. And it has the word math in it, which innately scares me because I am terrified of having to do math, especially on TV. I really don't want to have to do math on TV. So we're going to try to make this as simple as we can, try to break it down, try to make all of that pretty understandable, and then maybe, just maybe, we'll get to the math part at the end. So the first thing that we want to talk about is one of Charles Darwin's big ideas was this idea of evolution. Now, really simply stated, evolution just means that things change over time. Given a period of time and a thing, that thing can change. Doesn't mean that it will always change. Doesn't mean that there's a specific amount of time it's going to take to change. It just means that it's going to change. And I love to look at like cell phones because they're something that I saw during my lifetime. When I started off in high school and in college, there were no cell phones. And then suddenly in college, I started to notice towards the end of my college career, I started to notice these big, giant, what we would now call brick phones. And they're called brick phones because they were the size of a brick. They were huge. And you could put them up and you could take them with you and you could make phone calls from places that weren't in your house for the first time. And that was amazing because up until then, you had to make calls from your house or you had to go to someone else's house who had a phone. You couldn't make calls from your car. You couldn't make calls just anywhere. You had to be somewhere in someone's house where they had a phone. And so these big giant brick phones were pretty popular, but then people started coming out with phones that were smaller and weren't quite so bulky because the battery sizes started to get lower. And as those phones started to get smaller and smaller and smaller and smaller, they started to get more looking like the cell phones we started to see today. Until eventually there were the flip phones that you could flip them open and close them back up again. And they were really, really tiny. You could throw them in your pocket and you could carry them around with you. And that was pretty amazing. And that change happened over time. That technology that fueled that change made it possible for those things to happen over time. And so, as those things went along in time, you started to see differences in how these phones looked and how these phones behaved. And eventually, we started to see that we had phones that now had screens on them that you could touch, and you could watch things on them, and you could read things. And people were using phones for more than just talking to each other. They were using phones to do all sorts of other things besides just talking to each other. And so that was pretty amazing. But these changes that happened over time to these cell phones, they started to go in a different direction. Now you started to see cell phones get larger and larger and larger because we were watching things on the screens. And so the cell phone change over time really went in a number of different directions in a number of different ways. And it was so interesting to watch as a person growing up with cell phones changing in my own lifetime. So it was very cool to see that and very cool to see that change. And we have to ask ourselves, well, why do those things change? And as it turns out, cell phones changed because people bought more of the smaller ones. When you looked at a cell phone, you looked to see how big is that cell phone? Is it enormous? Is it tiny? And people looked at the tiny ones and said, ooh, I like that a little bit better. That's a nice small cell phone. I can fit that in my pocket. That's what I want. And so because they were selecting those smaller cell phones, the cell phone companies started making the cell phone smaller. So because of a choice that people were making, because of a selection that people were making, they were causing that change to happen in a very particular way. The change was pushing towards getting smaller and smaller and smaller things. Now, that's great for cell phones. It happens for music. If we think about what songs are on the radio, the more popular a song is, the more likely you are to hear more songs like that song. And I'm sure we can all think of songs like that, where when it comes on the radio, you're like, oh, it's this song. Oh, no, wait, it's that song. Oh, no, wait, no, 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 it's this song. And you can't tell the difference between them because they sound so similar. That happens because of this same selection. As we select things, people go, wow, if I'm producing music, I want to make my music sound like this hit that just happened. And so they do that and they change things and they make that change in response to what people are looking for. And so that is happened for cell phones, it's happened for music, it happens for fashion, it happens all over the place in a million things that we can think of. So this concept doesn't just happen in science, it doesn't just happen to animals and plants and things like that. It can even happen to ideas, and there's actually a word for that. It's called a meme. Now, some of you have probably heard of memes. You've probably even seen some memes on the internet. Memes, like we use them on the internet, are a word that describes like a picture that typically has some words over the top of the picture so that you can read a little message and it kind of goes with what's in that picture. And those pictures, a lot of times you can find the same picture with different words on it. The words change and the picture doesn't. And so what's happening here is you're seeing an idea. You're seeing the words that represent an idea and the change in that idea over time. And so now the picture that goes with that idea stays the same, but the idea is changing. And so they're referred to as memes. But memes originally was a word for scientists to use to describe ideas that are undergoing evolution, that are changing over time. Now, when we think about it in the context of organisms, that's where things start to get really interesting for scientists, for biologists, especially like me. When we try to think about why organisms change, I think for me, one of the things that helps me to think about it is to kind of use a representation like this. So this is my representation of these big chewy nerds jelly beans. I love these things. They're great. But not all of them are the same. Inside that jelly bean bag, there are some purple jelly beans, there are some orange jelly beans, there are some yellow jelly beans, and there are some pink jelly beans. Now, for me, I really love the purple ones, and I really love the pink ones, but I'm not so fond of the orange ones and the yellow ones. They're just not my thing. So when I reach into that bag, if I can look first and look around in that bag, I'm going to take a look and I'm going to look and see if I can find a purple one or a pink one. And I'm going to pull it out of that bag and I'm going to eat it. Okay, now we're going to have to make a little bit of a leap here. We're going to imagine that these jelly beans are actually little animals. All right, now hopefully it's not too gross for you to imagine that. But imagine that they can reproduce. Okay, imagine that they're animals and they can reproduce. They can make more of themselves. If I go in there and I eat a few of the purple jelly beans. Let's say I eat two of the purple jelly beans and one of the pink jelly beans. Okay. Now everything goes on as normal until jelly bean mating season comes around. Okay, jelly bean mating season comes around usually right before Easter. So jelly bean mating season comes around, and now the jelly beans are out looking for mates. And wouldn't you know it, in the jelly bean population in the wild here, we have 5 yellow jelly beans, we have 5 orange jelly beans, but we only have 3 purple jelly beans, and we only have 4 pink jelly beans. So it is very likely that when these jelly beans choose a mate, that the orange jelly beans and the yellow jelly beans are going to be more likely to reproduce because they're going to be in the majority of jelly beans. There's more of them than there are of the other jelly beans. So they're going to be more likely to reproduce. So after mating season, we might find that we get an extra orange jelly bean when a couple of orange jelly beans have a baby. And we might find that we get an extra yellow jelly bean when a couple of yellow jelly beans have a baby. But then the purple jelly beans, maybe they don't have any babies. And the pink jelly beans, maybe they get a baby. But at the same time as they're having a baby, another set of the yellow jelly beans are having a baby. And another set of the orange jelly beans are having a baby. And so now our population starts to look like this. And we see that we have way more orange and yellow than we have purple and pink. Well, now the next year comes along, and Mr. Alsop, the jelly beanivore, is out wandering around through the jelly bean preserve, and I happen to see a couple of jelly beans that I like, and I pick off a couple more of the purples and a couple more of the pinks, and then I leave, and I go on my merry way. And now when it comes time for jelly bean mating season again, there's a whole lot of orange jelly beans, a whole lot of yellow jelly beans, and almost no purple and almost no pink. So those purple and pink colors, because they're ones that I am choosing, things that I am selecting, the numbers of them in the wild start to go way down. But the orange ones and the yellow ones, because I'm not selecting them to eat them, their numbers start to go way up. This is what Charles Darwin started to notice when he was watching animals in the wild. He started to see this happening. He lived at a really interesting time in the 1800s when you could actually watch this happen because of things that were going on during like the Industrial Revolution. And he could see this happening. He could see that populations of animals, if you were selecting for certain things, they changed in very specific ways. But the next thing that he started to think about was a little bit more on the overall animal side of things. He started to think about that the key to all of this is survival. If you survive and get to the age where you can reproduce, then you are more likely to pass on those things that helped you to survive. So if you have something that helps you to survive, some difference between you and all of the other animals that are like you, that thing that makes you better at survival is going to get passed on to your offspring. And things that make you less likely to survive, like for example for my jelly beans, the purple coloring or the pink coloring, those are going to go away because they don't help you to survive. In fact, they make you less likely to survive. So when we look at survival, things that increase your survival tend to get passed on. So we look at this giraffe here, and I'm using this giraffe for a very specific reason. Some of you who are big science geeks will probably know why I'm using this giraffe. But the giraffe has a really long neck, and that really long neck helps him to survive. Now, that neck, that survival trait, how does he get that? Like, how do you get that to happen? Like how did that neck get to be that way? And the answer is it's all about mutations and it's all about randomness. So when we think about something like the giraffe, giraffes don't get to choose if they have a long neck or not. That's not something you get a choice in. Okay? You can't make your neck longer. Well, you can, but it's not going to get passed on to your offspring. That can only happen with a mutation in your genes. Your mutation in your genes is what's going to cause that trait, that longer neck trait, to show up. And those mutations are just random. It might be a trait for a longer neck. It might be a trait for shorter legs. It might be a trait for a bigger nose. It could be a trait for a lot of different things. And the mutations that cause those traits are just randomly occurring. We can't make them happen. We can't predict that they're going to happen. We can't guarantee that they're going to happen. They might happen, they might not. And when they happen, if they're good and they help you, then what's going to happen is they're going to get passed on to your offspring. And if they happen, remember if, not necessarily that they're going to happen, if they happen and they're bad for you, they're not going to get passed on to your offspring. Your offspring are not going to end up with those traits. So mutations that cause these traits are random. And in something like the giraffe, you've got a situation where one giraffe was born with a slightly longer neck, just like one human might be born with a slightly bigger nose. Those mutations are random. That giraffe got born with a long neck randomly. What happens after that is selection. And something will help that giraffe or will hinder that giraffe. If that giraffe is living somewhere and it has a slightly longer neck than all the other giraffes, and that helps it to get food, which makes it stronger, which makes it more likely to find a mate, then that giraffe will have more little giraffe babies, and you'll end up with that mutation being in more giraffes. And then if those giraffes over time, soon maybe those giraffes are going to have more babies than the other giraffes, and pretty soon you're going to have a situation where all the giraffes have that same mutation because it's so beneficial that giraffes that don't have it are less likely to live and less likely to continue to succeed. And so now you have a situation where that trait has become the norm. And that's going to keep going from generation to generation to generation. Now, maybe if that neck trait mutated once, it could mutate again, and you could get giraffes with even slightly longer necks, just like you can have people with even slightly larger noses. If everyone had large noses and then people were all, looking at everyone and everyone had large noses and that was considered to be really attractive, and then all of the large nosed people started having offspring, maybe there would be some offspring born with a super huge nose. Same way you go with giraffes, except for in that case, it's not to have to do with their looks. It's to have to do with being able to find food and being able to be more successful. So there is something that has to choose, and that something that does the choosing is nature. It's the ability to survive, the ability to live, the ability to have more offspring. And the world around you helps shape those opportunities. And so that's why we call this natural selection. It's because nature is doing that selecting. Now, we as human beings, we've done this for some species ourselves. We've done human selection, okay, what we call artificial selection for certain species, where we've said, oh, we really like dogs, and we really like our dogs to have really big eyes, really close set in the center of their head. And so we found dogs that had eyes that were bigger, and we made sure that they mated with other dogs that had eyes that were bigger to try to get dogs with bigger eyes. And then you end up with things like a pug, a little dog that has really big eyes and they're set close to the center of the head and everybody thinks they're really cute. And we created that on purpose by selecting. Well, nature does this too, but it's not necessarily on purpose. When natural selection happens, it just happens because the environment around you is difficult. And the environment around you being difficult is going to cause some of your traits to be good for you and some of your traits to be bad for you. And those good traits are more likely to help your survival, and those bad traits are more likely to hurt your survival. And so you stick with it with the good traits, and they stay in you, and those bad traits will gradually start to go away. So nature is doing all of this selecting. Now, I told you at the very beginning, when we got to the end, we would have to think about math for a minute. And Mr. Alsop really not so great with the math thing. But I just want to bring the math into this a little bit. The math that we're talking about here is probability. Now, probability is that thing that tells us what is the chances of something occurring or not occurring. So it figures in the mutation side of things, where the mutations, maybe they occur, maybe they don't occur, what's the percentage chance for a mutation. But it also changes with the idea of how you might be born with a trait that's positive for your survival. What is the percentage chance that that trait is going to get passed on to your offspring? And so as we start looking at these things, we can actually start using math to figure out how likely it is for a trait to get passed on in a population. We can look at a population like this one, and we can see that in this population, what is the percentage chance that in the next generation we are going to see more orange and yellow and less purple and pink? How does that work? We know what's happened in previous generations. Now let's take that and move forward to another generation. And when we look at what they wanted us to know, what they wanted us to be able to do was use a mathematical representation for this. And so what we have to think about is what kind of math using probability can help us out to figure out how the population is going to change and how those traits are going to increase and decrease over time. And the basic answer to that is just that the more beneficial a trait is, the more a trait is good for you as an organism, the more likely it is for it to be passed on. That's the basic math that we're looking at here. So if you get a chance, take a look on the internet for math and populations and evolution, and take a look and see what you can find out about the mathematical equations that drive that. And hopefully, maybe next week, we can talk a little bit more about the math and the equations that drive evolution and that drive the change in traits in a population over time. Thanks for coming and listening to Science for the Week. I will see you guys next week.